Hello, welcome. Welcome to a new video. In this video, we are going to prove two important results in metric space. First result is the open subset of the metric space XD have the following properties. First property is first property says that X and the null set are open sets. The second property says that the union of any family of open sets is open. Here we consider any family, that means the collection of open sets that we take may be finite or infinite. See, the union of any family of open set is open. But when we come to the third statement, we must strictly take only a finite family of open sets. So the intersection of we take the intersection of that open sets. The intersection of any finite family of open set is also open. We are going to see the proof of the statements one by one. First, we shall prove the statement 1. The entire space X is open since it is the union of all open balls of all possible centers and ready. See, the entire space X is open. Why? It's because of the reason that it can be written as expressed as the union of all open balls, all possible open balls of all possible centers and ready. Okay. But the empty set, the null set is open since it is the union of only an empty collection of open balls. See, the null set contains no points, so there is no chance of getting an open set from the null set. So in this case that result follows trivially. Okay. Yeah, this is an example of a trivial proof. Okay, next we are going to prove the statement 2. The union of any family of open set is open. The union of any family of open set is open. For this, we have to consider an index set. A. Here A is the index set that contains numbers 1, 2, 3, etc. That is used to give numbering to the open sets. So we take the open sets, the collected open sets are numbered 1, 2, 3, etc. So O1, O2, O3, etc. according to the numbers in the index set. We know that we also know that every open set in a metric space is the union of open balls. See, every open set, you have to recall that from the definition it is clear that every open set in a metric space can be expressed as the union of open balls. So applying that, we get each open set here. Here we consider, since we have taken O1, O2, O3, all these are open sets, so each of these open sets can be expressed as the union of open balls. So when we consider the union of these open sets, that is union taken over all I of the open sets, that can also be written as the union of open balls, because by considering each open ball that make all open balls we consider that make the open sets one by one, and then we can take the union of all those open sets to obtain the entire union. The whole union can be written as the union of open balls. So we get that that union is also an open set. Coming to the third statement, we are restricted to take only finite number of open sets. So we consider a finite family of open sets, so we can label the open sets as U, O1, O2, O3, etc. to On. We take them and we define in the intersection. We have to take the intersection of according to that statement, we have to take only the intersection of that open sets, that is intersection I equal to 1 to I equal to n of OI. Next we want to show that we want to show that this set is open. For proving that, we consider a point of this intersection. Let x be a point of this intersection. Then you can see that that taken point, which is a point of the intersection x, that belongs to each open set, because it is taken from that intersection. So x is an element of the first open set O1, x is an element of the second open set O2, and etc., etc. Okay, therefore since each next we can say that we can find an open ball. Then when we consider the first open set and the presence of x in O1, you can find a positive real number epsilon 1 such that the open ball defined, that is bx epsilon 1. See, this is the open ball which is centered at x and that has the radius epsilon 1. So there exists an epsilon 1, a positive number epsilon 1, such that bx epsilon 1 is centered at x and that is contained in O1. Bx epsilon 1 is a subset of O1. This argument can be applied in the case of the second open set O2. But in that situation, in that case, we can find a different real positive value, epsilon 2, which is given the name epsilon 2, such that the open ball bx epsilon 2 is centered at x and bx epsilon 2 is a subset of O2. We can apply the similar argument can be applied in the case of every open set up to the last open set On. In each case we get an open ball and the real number is epsilon 1, epsilon 2, etc. to epsilon n, and finally we take a single real number by defining minimum by taking the minimum of all the existing epsilon values. That is, we are taking epsilon equal to a real number epsilon, and we are defining a real number epsilon equal to minimum of epsilon, all epsilon, minimum of epsilon I. Actually the I is missing, so minimum of epsilon I, where I varies from 1 to n. And this is a real number. Clearly it's a positive real number, and we are now defining. We can define bx epsilon, a new ball, bx epsilon. Clearly this bx epsilon contains x, and it is contained in each OI, in each open set. So when we define when we consider the intersection of all open sets, see, you can see that that open ball bx epsilon, that open ball is contained in the intersection of all OIs. And also it contains the point x. So we can say that, we can conclude that the intersection of OI, intersection where I varies from 1 to n of OI, is an open set. See, next result that we are going to state and prove is about the closed sets that exist in a metric space. But those results seems to be very similar to. It resembles the set of the set of three results that we have stated and proved in the case of open sets. But of course there are some differences. Some very serious differences are there. See, the first statement, you can go through the statement. Let us consider the closed subsets of a metric space XD. We have the following properties. The first statement says that X and the null set are closed sets, and the second statement is that states that union of any finite family of a closed set is closed. See, union of any finite family of closed set is closed. And the third statement is that takes the intersection of any family of closed set is closed. See, that says that intersection of any family of closed set is closed. When we think about the proof of this statement, we can say that the proof can be developed using the method of complement. That means throughout this throughout the proof of throughout the steps, we consider complement of open sets. So coming to the first coming to the proof of the first statement, see, we know that when x is closed, its complement, what is the complement of x? It is the null set, because x is the whole metric space, so its complement will be the null set. And since x is closed, then then okay, and since we have to show that we have to state that x is closed. See, we know that the complement of x is the null set, but we know that using the previous result, in the previous result we have proved that we have stated that phi is open. Phi means the null set is open. Since the null set is open, its complement is x, so that must be closed. Similarly, since we have seen that x is open, x is also open, x is open, so it's since and its complement is the null set, therefore the null set phi must be closed. Hence we can complete the first part of the first statement. Then the proof of the second statement. Here we have to consider union. We have to consider union of any finite family of closed sets. So we take a set of closed sets C1, C2, C3, etc. to Cn that contains only finite number of closed sets. After that, we define the union of these closed sets C1 union C2 union etc. to union Cn, and we give a single name for that C. Also, we take C is equal to C1 union C2 union etc. union Cn. After that, we apply complement on C, and that is C complement is equal to C1 union C2 union etc. union Cn, the whole complement. But you can apply that that reversal property, that we get that C1 complement, it is equal to this is equal to C1 complement intersection C2 complement intersection C3 complement intersection etc. to Cn complement. Okay. That union is then reversed to intersection. Okay, then now when we analyze this, the right side, you can see that these are when C1 is closed, then C1 complement is open. Okay, so it is the and this expression it's a finite intersection of open sets. It's a finite intersection of open set C1 complement intersection C2 complement intersection etc. Intersection Cn complement, and therefore this intersection, this entire the whole intersection is an open set. So it's an open set. That means C complement is an open set, and since C complement is an open set, we can say that C is a closed set. Okay. Next, to prove the third statement, we consider an indexed set of closed an indexed set of closed sets. See, I is an index set that contains numbers 1, 2, 3 etc. up to infinity, and corresponding to that numbers, we take the closed set C1, C2, C3 etc. up to infinity, and after that we define the single set C is equal to the intersection where I varies in A of Ci. So intersection of Ci, actually it is intersection of Ci of all Ci's. And then we take the complement of C, apply the complement of C, then it becomes intersection where I varies in A of Ci, the whole complement is equal to union, then that intersection then revises to union. So union over I, union where I varies in A of Ci, what happens to that C then becomes complement, Ci complement, the union of Ci complement. And you know that in the previous result we have proved that union of any number of open sets. See, union of of any number of open sets, or any family of open set is what it's open. So see, this union is open, this set is open, the right hand side set is open. So the first set, left hand side set is also open, and that is C complement is open, and hence you can conclude that C is, since C complement is open, C must be closed, and thus we get that C is closed. Okay, by this we can conclude that the proof of the second result. Okay, and that's the end of the proof of the all the three statements. Yeah, thank you for listening.